Hello everyone, my name is Mehmet and my teammates are Emre Asil and Cağan Haksal. Our project supervisor is Metin Muradoğlu. Our project is Bladeless Wind Turbine. Our goal is to harvest wind energy with using vortex shading. We use coil magnet system and generator and pulley system. The system has a benefit of large implementation area, low manufacturing cost and less maintenance cost. It operates with less noise so it can be used in urban areas. Since the last meeting, we have completed the battery circuit board and connections of generators. We have calculated the spring constants. First, we have used hooks to set the springs. However, it did not look safe, so we have added the side plates. We made the tips of the springs straight and drilled a hole inside the side plates with an angle to place them safely. So the side plates have made the platform more durable and helped us to fix the springs. The springs have helped us to center the pipe after a motion, and they hold it 90 degrees when it's not moving. Here is our calculations for the springs we needed. We have started by computing the limit angle of the pipe. This is important in few ways because after a certain angle, the springs yield so much that the springs deform, or springs may not be able to center the pipe back, or with an unstable placement, the system may fall over because of the center of gravity exceeds the turning point. According to these data, we have determined the safety angle is maximum 67.5 degrees. We first thought of connecting the springs to the bottom of the rod because we needed stoppers at the top side of the platform. However, the force was too high for the short length. This ended up breaking the rod. We switched to a clamp system on the pipe. This was a successful attempt. When buying the springs, we have visited few shops to find a spring with a constant we have calculated. We wanted it to yield in only tension, not compression way. With that, we solved the need for the stoppers.
This is our NX CAD design. We used a PVC pipe for the pipe in the middle, and rest of the parts are 3D printed PETG plastic, except the rod, bearing, and the belt. I want to start by explaining how the motion system works. First of all the oscillation motion captured by the pipe moves to central hub, which has two big pulleys connected to each side. Central hub is carrying everything and is connected to the platform using an 8 mm steer rod and two beefy bearings that is shown on the left bottom. Two generator mounts that are each carrying two generators are also connected to the both sides of the platform. 3D printed belts, which are made from Shore 85A TPU material, are connecting the big pulley to the small generator pulleys. This allows the motion to be transferred to the generators, resulting in an AC current. We connected all the generators in series to increase the total voltage output. This resulted in a voltage between plus and minus 2.2 volts. Based on this test, we created a circuit design which has full bridge rectifier in it to convert this AC current to DC. Doing this conversion results in some voltage loss around 0.7 volts because of the diodes. However, our generation has some headroom, so it's not a problem. We also added functionality LEDs to see the device working. You can see our final circuit design below. With the circuit, we can charge a 1.5 volt nickel AA size battery.
In static analysis, firstly we performed structural analysis on rod and found that we have averagely 1.7 times 10 over minus 2 millimeters total deformation, and 7.5 times 10 over minus 5 elastic strain, and 1.3 megapascal equivalent stress. Secondly, we performed structural analysis on our pipe and found that we have averagely 3.3 times 10 over minus 2 meter total deformation, 2.3 times 10 over minus 3 elastic strain, and finally 7 times 10 over 5 Pascal equivalent stress. In the CFD analysis, firstly, vortex shedding effect occurs between Reynolds number 300 and 3 times 10 over 5. So our design parameters were set to stay in that region. We designed our prototype with a 16 centimeter pipe diameter and 1.5 meter at length. With these parameters, we calculated Reynolds number of our prototype as 5.4 times 10 over 4 at 15 meters per second wind velocity. And by using Storal number, which is on top right corner, Vortex shedding frequency was calculated as 6.18 Hz. For the results, we took measurements in every 30 minutes in a total duration of 5 hours, and we found that when there is an average 7.7 meters per second wind velocity, our prototype generates averagely 0.65 watts. In this project, we tried to construct vortex shedding bladeless wind turbine. Due to the budget constraints, our electrical system is not strong enough for the kinetic energy we are collecting. With a better suited electrical system, we can improve the overall production efficiency of the system. Lastly, more suitable generators that require lower RPM should be used. Thank you for your attention.